This video continues from my video on chemical equations. To learn about chemical energy, we need to discuss enthalpy and internal energy. Released or absorbed energy during a chemical reaction can come from the breaking of old bonds and the formation of new bonds. This energy could also come from a phase change, such as when a solid melts into liquid or when a liquid boils into a gas. The extra energy absorbed by a substance when its solid form melts into a liquid can be called its latent heat of solidification or its enthalpy of fusion. The extra energy absorbed by a substance when its liquid form boils into a gas is called its latent heat of evaporation or its enthalpy of vaporization. Energy absorbed as a substance increases in temperature at a constant volume is called its increase in internal energy. Internal energy is often symbolized by a small u or a capital U. Energy absorbed as a substance increases in temperature at a constant pressure is called its increase in enthalpy. Enthalpy is often symbolized by a small h or a capital H. 298 Kelvin or 25 degrees Celsius is often used as a reference temperature for room temperature. Any internal energy difference of a substance from its reference temperature internal energy might be symbolized by U minus U ref. Any enthalpy difference of a substance from its reference temperature enthalpy might be symbolized by H minus H ref. Enthalpy is the sum of internal energy plus pressure times volume. An enthalpy change equals an internal energy change plus any work done to the surroundings by a pressure change or volume change. The total internal energy of a substance can be written as an integral of its heat capacity at a constant volume, as shown in the equation. U is the total internal energy of the substance, X is the number of moles, Cv is its heat capacity at a constant volume, and T is the temperature of interest. At the temperature of interest, the internal energy of a substance is U equals X times Cv times T. The total enthalpy of a substance can be written as an integral of its heat capacity at a constant pressure, as shown in the equation. H is the total enthalpy of the substance, X is the number of moles, Cp is the heat capacity at a constant pressure, and T is the temperature of interest. At the temperature of interest, the enthalpy of a substance is H equals X times Cp times T. The energy unit for internal energy and enthalpy can be given in joules in the SI system, or calories, kilocalories, or BTUs in the British system of units. Tables of heat capacities for many chemical species can be found online or in the backs of most chemistry books. If the mole fractions of products are known, or even guessed, the heat capacity for each product can be weighted by their mole fraction and summed to get a combined heat capacity for the product mixture. Once we add up the enthalpies of the products, we can get the temperature of the reaction by rearranging the enthalpy equation as shown. The bond strengths at 298 K of some common propellant reactants and products are listed in the table. The bond energy is how much energy is released when the bond forms. The bond energy is also how much energy is needed to break the bond. This bond energy is included in the enthalpy change of the product of reaction. We call the bond energy contained in a molecule or system of molecules its enthalpy. When a group of free atoms bond to form molecules, heat is given off. The enthalpy or energy contained in a group of molecules is less than the free atoms that they were formed from. Nature is always trying to get into a lower energy state. If 2 moles of free oxygen atoms react, and pairs of atoms of the group bond to form 1 mole of oxygen gas molecules, O2, 118.4 kilocalories of heat is released. The 1 mole of oxygen molecules contains 118.4 kilocalories less energy than the 2 moles of free oxygen atoms had. The enthalpy change is negative 118.4 kcals. Conversely, to break up 1 mole of oxygen gas into its component atoms, you must add 118.4 kcals of energy. The enthalpy change to the system is positive 118.4 kcals. So 118.4 kcals of heat must be added to break up 1 mole of O2 into individual oxygen atoms. This proves that the more stable form of oxygen is the combined state, O2, with less energy. A system's enthalpy change can be plotted on an enthalpy diagram. In the enthalpy diagram shown, we show the reaction of 1/2 H2 plus 1/2 F2 to form HF, hydrogen fluoride. For the reaction, first break up the hydrogen gas into individual atoms. Add 52.1 kcals of energy. Next, to break up the fluorine into individual atoms, add 18.3 kcals of energy. So the energy added to dissociate the reactants is 70.4 kilocalories. When these 2 moles of free H and F atoms bond to form 1 mole of HF, 134 kcals of energy in the form of heat is released. The change in enthalpy from the initial state to the final state is the energy added minus the energy released. 70.4 kcals minus 134.6 kcals equals negative 64.2 kcals. The change in enthalpy between the initial state and the final state is negative 64.2 kcals. We say that the burning of 1/2 mole of hydrogen gas with 1/2 mole of fluorine gas to form 1 mole of hydrogen fluoride releases 64.2 kilocalories of heat. And that concludes my discussion of enthalpy and internal energy. In my next video, I will focus on gas-gas reactions in combustion. Thank you for watching. If you enjoyed my video and would like to help me make similar content, please hit like and subscribe.